In this video, we're going to look at some applications of radian measure, but we can also look at this in terms of degree measure. We're going to be looking at arc length and area of a sector. Arc length is just a fraction of the circumference of a circle. So if we think about a circle, that exterior length is our circumference. The arc length is just the measure of one piece. Now that one piece is related to the angle that we've created between or within that circle. So when we think about arc length, which we're going to use the variable s to represent arc length, it's going to be a fraction of the circle times its circumference. Remember that word of in math often translates to multiplication. So theta over 360, this is if we're measured in degrees of the circumference, which is 2 pi r. So this formula is used if our angle theta is in degrees. The other version of this formula, theta divided by 2 pi times 2 pi r. And that theta over 2 pi is talking about the fraction of our circle if theta is in radians. Now, both of these formulas can be simplified, but once we simplify them, it becomes a little bit more challenging to remember them. So if we're thinking about arc length as just a fraction of the circumference, your fraction is dependent on the number of degrees out of the entire revolution, regardless of whether or not it's in radians or in degrees, multiplied by the circumference. So this is why I'm choosing not to simplify those formulas, just to maintain that intuition of how to set them up. If a circle has a radius of 18.2 centimeters, find the length of the arc intercepted by a central angle of 3 pi over 8 radians. Now, this is pretty straightforward, so I don't necessarily need to draw a picture, but we know that the central angle is 3 pi over 8, and the radius is 18.2. So starting, we're just going to set up our radius of 18.2, and then a central angle of 3 pi over 8. I'm not going to worry about how large that angle is. I'm just going to set up a picture. So here's, let's say 3 pi over 8. Maybe this is a very accurate drawing. Maybe it's not really that important for this particular example. Our arc length is going to be the fraction of our angle. So 3 pi over 8 divided by 2 pi times 2 pi times our radius, which was 18.2. Now I'm going to start doing some simplifying before having to multiply across. These factors of 2 pi are going to cancel out, leaving us with just the 3 pi over 8 times 18.2. And when we're finding the length of an arc, oftentimes we do not leave it in terms of pi. We are going to evaluate it as a decimal, but try to make sure you use that pi key on your calculator rather than using an approximation for pi like 3.14. It just makes your answer at the end even more accurate since we're probably going to round anyway. So multiplying across, this is 21.44 centimeters. Reno, Nevada is approximately due north of Los Angeles. The latitude of Reno is 40 degrees north, and that of Los Angeles is 34 degrees north. The radius of the Earth is 6,400 kilometers. Find the north-south distance between the two cities. A quick note, latitude bearings are measured from the center of the Earth / the equator. So we're going to be measuring them from our horizontal. So again, that idea that this latitude, this is just a new bearing method. So if I think about the Earth, and I'm going to draw this two-dimensionally, but it's important to remember that the Earth is a three-dimensional sphere. Here's the center of our Earth, and here's our auxiliary compass. So Reno, if we think about the latitude being 40 degrees north, we're going to start with this positive x-axis or that due east and go 40 degrees in the north direction. So Reno is going to be approximately here, where this angle is 40 degrees. Los Angeles is 34 degrees north, or the latitude of Los Angeles is 34 degrees north. So I'm going to use a different color just to make it so it's a little bit easier to read. From that horizontal going up 34 degrees. And I'm separating it or exaggerating this difference just so we can see it a little bit easier. Here's LA. And this angle is 36 degrees. I'm sorry, 34 degrees. So I'm going to redraw this picture just to bring out some of those extra information we don't really need. So we've got Reno here. We've got LA here. And if we use those two bearings that we were given, we can see that the angle between Reno and LA is going to be 6 degrees, since Reno had 40 degrees and LA was 34. If we subtract 34 from 40, this is our 6-degree angle. What we're looking for is the north-south distance between the two cities. So what we're really looking for is this distance. Now, I realize in this two-dimensional figure, it doesn't look directly or due north. Reno doesn't look due north of LA, but if we were to think about this in terms of a sphere and face it towards us, we would see that LA lies directly south of Reno, or based on what the problem's saying, Reno is due north of LA. We're told that the radius of the Earth is 6,400 kilometers. So now we can find that distance between the two cities. This is our arc length. It's our fraction of the circle, so 6 divided by 360 degrees times 2 pi times our radius, 6,400 kilometers. We're just going to multiply all this through, including that factor of pi using the pi key. And this gives us 670.21 kilometers between Reno and Los Angeles. Two gears are adjusted so that the smaller gear drives the larger one, as shown below. If the smaller gear rotates through an angle of 225 degrees, through how many degrees will the larger gear rotate? Well, if we envision these two gears moving at the same time, the length that's created between those two gears is going to be the same. So we know the arc length of the small gear is equal to the arc length of the large gear. So we're going to set up formulas for both of these to determine our unknown of the central angle from that larger gear. So the arc length of the small gear, it's rotating through an angle of 225 degrees. So this is 225 divided by 360 times the circumference, 2 pi r, which is 2.5 centimeters. This arc length is equal to the arc length of the large gear, which we don't know what theta is. But we're going to keep it in terms of degrees because our first angle was in degrees. So theta over 360 times 2 pi times the radius of the large gear, which is 4.8 centimeters. Now we're going to do some simplifying before moving through with this problem. First, I'm going to divide both sides by 2 pi. If I divide both sides by 2 pi, we see that that common factor will cancel out on both sides. We're going to simplify the left-hand side since we have no more variables. 225 divided by 360 multiplied by 2.5. We're going to leave this as a simplified fraction. So this is going to be 25 over 16. And this is equal to theta over 360 times 4.8. Now to get theta by itself, we're going to multiply both sides of this by 360 divided by 4.8. On the right-hand side, those coefficients cancel out. And multiplying across, and we will use a decimal here, this becomes 117.19 degrees. Area of a sector, we're going to look at this in the same way we looked at arc length. Area of a sector is just a fraction of the area of a circle. Area of a circle, the formula is pi r squared. So the area of a sector is equal to the fraction, so theta over 360 times pi r squared. This is if theta is in degrees. Or the area of a sector is equal to theta over 2 pi times pi r squared if theta is in radians. Similarly, we might be able to simplify these a little bit, but we're not going to, just to maintain that intuition of how to set up these formulas. A center pivot irrigation system provides water to a sector-shaped field with measures shown below. Find the area of the field. So the length of that irrigation system is going to be 320 meters, and it's going to provide water for a sector that has a central angle of 15 degrees. Since we're being measured in degrees, the area of this sector is going to be 15 over 360 degrees times pi times the radius squared. Plugging this into our calculators or into Desmos, this is 1,000 or 13,488.04. And when we're talking about area, our units are going to be that unit of length squared. So this is going to be meters squared. A circular sector has an area of 50 inches squared. The radius of the circle is 5 inches. What's the arc length of the sector? So we are dealing with a portion of a circle, which again, I'm not going to get into how accurate this figure is, but just to illustrate the information being provided. So we have a sector whose area is 50 inches squared. We know that the radius is 5 inches. What we're trying to figure out is that arc length. So I'm going to set up my formula for arc length using radians. So we're trying to find the length of the sector, which is going to be theta divided by 2 pi times 2 pi r. Now within this, we still don't know theta, but we do know the radius of our circle is 5 inches. So we can simplify this a little bit. But what this illustrates is what we're trying to figure out is theta first. And theta is that central angle. So we're going to use that area of a sector formula to figure out theta, which then we can substitute into this arc length formula. So that area is 50 inches squared, and that's equal to theta divided by 2 pi times pi r squared. So I'm going to use this equation to solve for that central angle theta. I'm going to start by simplifying this before moving forward. So 50 is equal to theta divided by 2 times the radius, which is 5 squared, or we can do that mentally, 25. Multiplying both sides by 2 over 25. Two over 25 times 50 is 100 divided by 25, or 4, is equal to theta. So this is in radians again, because we started with our formula in terms of radians. Had we set this up as theta over 360, we would have gotten a different answer here, but it would have been in terms of degrees. So equivalent angle measure, just different units. So now we can solve for our arc length. Our arc length is going to be 4 divided by 2 pi times 2 pi r, or 10 pi. Because 2 times 5 is 10. We're going to start simplifying this. 10 pi divided by 2 pi is 5. So our arc length is going to be 20. And this is in terms of inches.